Last time, we started to use Hostin-Primakov bosons to represent to re-express this Heisenberg ferromagnet on simple lattice, and we Fourier transform this so-called Hostin-Primakov bosons and a dagger, and which are related to the spin operators, S plus, S minus, and also S z. And after we Fourier transform the Hamiltonian, the Hamiltonian is given by this constant epsilon 0 plus sum over this normal mode h bar omega q a dagger q a q, where this omega q is called the magnon dispersion of magnon frequency as a function of q, with omega 0 depends on external field. And the most important factor is this, this last one, h bar times j0 minus jq, where j of q is a Fourier transform. This coupling constant is Heisenberg nearest neighbor interaction. So the j of q is the Fourier transform of this JLL prime, and when we do so and subtract from this j0, this term j0 minus jq is given by this sum over nearest neighbor L prime of JLL prime for a fixed L, and times sine square 1/2 of q dot this displacement vector L minus L prime, and there's a factor of 2. And we could just work things out by using the different lattice structures in different spatial dimensions to really work out this summation over nearest neighbor L prime. So for example, in one dimensions, the coordination number, which we call z, is 2 because there are two nearest neighbors. And in 2D, we have 4 neighbors on the square lattice, and in 3D, z is 6 on the cubic lattice. And after plugging this a coordination number in different spatial dimensions, we could Taylor expand this omega q for small q. And in particular, for one dimension, h bar omega is given by 2 times j times s, where s is just a spin. For example, for spin 1/2, this is just 1/2. And 2js times a square q square, because this is sine square, so you could easily just do Taylor expansion of the sine square, and you take care of this prefactor. L minus L prime is just plus minus a for nearest neighbor L and L prime, where a is the lattice spacing. All right, so that's how you get this sine square qa, and you expand this sine qa, you get square of this a square q square times this prefactor 2js, and we define this prefactor the factor other than q square. This is what we call this spin stiffness constant, capital D, which is a prefactor in front of this q square dispersion. In general, for general dimensions, this h bar omega q is given by j z s a square q square, where z is just what we just defined here, this coordination number. It depends on this lattice structure and dimensionality, but in general, this is the dispersion for a magnon excitation for a ferromagnet. And this is a quadratic dispersion as shown here. And the capital D is called spin stiffness constant, which measured how easy or how hard that we could have such spin excitations. Okay, for a given value of q, you can see that when D1 is larger than D2, you get more, the higher frequencies or energies that is required to have such excitation for a larger value of d1. So for a larger d, it means that it's more difficult to have such a spin excitation because it takes a larger amount of energy. But for small spin stiffness constant, it is very easy to excite this magnon in the system. So we could use this formalism to calculate the amount of spin excitations in terms of Hauss-Impermeable bosons. Remember that this Sz in the Hauss-Impermeable representation is given by h bar times 1/2 minus n, where n is number of bosons. And the number of bosons represents the number of spin flips. Remember that this S plus S minus are given in terms of this Hauss-Impermeable bosons, right? Okay, so if you destroy the Hauss-Impermeable bosons, you actually get a spin flip S plus from the spin down state to spin up state. So the number of A, or number of spin flips, measure the the number of this kind of spin flip events, and therefore this n, which is A dagger A, measures the number of Hauss-Impermeable bosons and also the number of spin flips. So there's a one-to-one correspondence between the spin flip and Hauss-Impermeable boson number. So to really calculate this, the net mechanization at finite temperature, which is due to the spin flips at finite temperatures, and we could sum over all the Z spin angular momentum for all this site L, and when we do so, we get 1/2 of h bar times the number of spins, okay, subtract by this number of spin flips. When we have a spin flip, what will really change the spin angular momentum is actually 1 h bar. Remember that. When we have this, 1 A dagger A refers to the fact that we actually flip the spin, say from spin down to spin up state. So therefore, the net change of the spin angular momentum on the z-axis is actually h bar times NL. All right. So for pure ferromagnet, in the absence of the spin flips, everybody, is perfectly aligned along a particular direction, say plus z. Suppose at finite temperatures there's a spin flip event. What it does is to decrease the amount of a spin angular momentum at z along z-axis by the amount of n times h bar. Suppose A dagger A is actually just 1, then this will just change the spin angular momentum at z negatively by 1 h bar. Okay, this is understood in terms of this kind of a cartoon picture. Suppose I flip the spin, from the up spin state to down spin state once, which means that I, have this 1 Hauss-Impermeable bosons. Okay, once we have this, A dagger A being 1 as a average value, then this spin is going to be flipped to spin down state from spin up state, and therefore there's a total change of the spin angular momentum at z, which is minus 1 h bar. Because before the spin flipped, the spin stays actually pointing up, and after the spin flip, it is pointing down, and therefore the delta S z is actually minus 1/2 h bar minus plus h bar over 2, which is minus h bar. If you have, n multiple spin flip events happening here at finite temperature, then the total amount of Sz is given by the non-split maximum value, which is 1/2 h bar times capital N, where capital N is the total number of spins, and subtract by the number of spin flips. And each spin flip will cost you minus 1 h bar. And if you sum over all possible spin flips, and you should subtract this integer number of h bar from the total Sz. And so we could rewrite this kind of a net mechanization in this form that mz is the a net mechanization at any given temperature, which is given by 1/2 h bar, which we call this mu b, times number of spins subtract by 2 times the spin flip, or the Hosteen-Perlmutter bosons. And you could simply just re-express this in terms of the delta mz, which is the deviation of this mechanization from the maximum value at 0 temperature, and which is given by 2 mu b times sum over q and q, where nq or nq bar at finite temperature is nothing but the thermal average of this boson occupation number, which is given by this factor here, the Bose factor. And in the energy, in the denominator, we get e to the h bar omega divided by kBt, where this omega, is nothing but this omega here, or omega here, which is quadratic proportional to q. So we should sum over this m bar q over q, which is sum over this Bose factor, and this inside the summation, this omega takes this quadratic dispersion, and so you plug in this quadratic dispersion and sum over the 3-dimensional Q space. You end up been doing this kind of dx integration, and inside the integral, this is square root of x divided by e to the x minus 1, where the x is defined by this dimensionless quantity or variable capital dq squared divided by kBt. And the integration over x is just a constant, some special integration constant. And the most important part of this calculation is this temperature to the power of 3/2 for a 3-dimensional ferromagnet. And this is something that could be checked experimentally, and we call this Bloch's law of spin waves or magnetic excitations of a ferromagnet. Okay, so at low temperatures, if you subtract this your magnetization at finite temperature from this maximum value m0, you'll get temperature to the power of 3/2 relation. And it is precisely the case in experiments that if you measure delta m z at the function of temperature divided by this maximum of a spin moment m0, and you make a plot against t to the power of 3/2, you get a straight line. And this is the more precise result of delta m over m0. Sorry, this should be 1 minus, because when temperature is 0, there is no delta, and so everything should be normalized to 1. But when temperature increases, this amount, delta m, increases. Therefore, this 1 minus delta m divided by m0 will decrease. And so this is your homework. You could check your reference to derive this more accurate, more precise results, which is this kind of a numerical prefactor 0.05 divided by the size of spin, and also divided by the q number, which is the coordination number, and times this kBt divided by 2js, everything to the power of 3/2. Okay, so this is a straightforward calculation, and you could easily evaluate this. Okay, so let's take a short break. When we come back, we will start another calculation, which is the Heisenberg antiferromagnet. Okay, so let's continue. Before we study the antiferromagnet, let's just do this simple exercise for a ferromagnet at finite temperature, and in particular, we will evaluate again, say, the number of spin flips event or the change of the spin angular momentum or magnetization delta m per site for this ferromagnet. You'll see that this kind of a change in magnetization per site will diverge in the low dimensions. By saying low dimensions, I mean for d equals to 1 and d equals to 2, for one-dimensional, two-dimensional Heisenberg ferromagnets, this delta m will diverge, in the thermodynamic limit and also in this low temperature limit. And that's really, very important point for the spin wave theory, that the spin wave theory will break down because we assume that the change of magnetization due to spin flips at low temperatures is actually tiny or negligible. So we could safely assume that delta m is just a small perturbation. However, this is not true in 1D and 2D system. So that's why we're doing this exercise right now. So let's just again compute this number of spin flips or number of Haustein permeable bosons in momentum space, and we sum over all possible nk for all k and divided by the number of spins, which is the delta little m per site, and this nk satisfies this Bose factor. When we do so, we could just separate the sum in terms of two terms. One is the integration over the k from the small value k0 to the sum finite value k bar, and the second term is we go beyond k bar to almost infinite k. So the reason why we separate these two summation or integration will become clear in just a moment. Okay, so in this small, if this magnetic dispersion compared to this thermal energy kBt is much smaller than the kBt, and also this k bar squared times j times s is actually order of magnitude of h bar omega k bar, then, and this is actually much smaller than the j times s in that regime, we could do Taylor expansion with denominator e to the h bar omega divided by kBt minus 1 could be Taylor expanded, and we collect just a leading order term in omega over t. So in other words, when omega over t is small, we can do Taylor expansion. And when we do so, we plug in this Taylor expansion up to leading order in this small k regime, and we'll find that when this lower bound k0 approaches 0, and this integral diverges for 1 and 2 dimensions. And the second term still remains finite, but the first term will diverge when k0 approaches 0. So let's just do it. So let's do it for the first term. We plug in this Taylor expansion, and in one dimension, this is, say, k to the power of d minus 1, where d is 1, and this is just a constant divided by 1 over k squared, and integrated over from k0, where k0 is from 0 to some finite value. So, but we still keep this k0 as a small lower bound here, but then this delta m depends on the lower bound k0 in this fashion, and also this dimensionless temperature little t in this fashion, which is minus t over k0. However, you know that k0 is just a small momentum cutoff, so-called infrared cutoff, and this corresponds to the size of the system. When k0 approaches 0, this means that the size of system approaches infinity. Okay, and therefore, when k0 approaches 0 in the thermodynamic limit, where your system size becomes infinity, then this T over K0 is actually infinity. The whole thing becomes infinity, and therefore the net magnetization change for one-dimensional Heisenberg ferromagnet is actually infinity. But that can be correct because we assume that this delta m should be small from the beginning. However, this estimation is actually accurate. So which means that this assumption here, that delta n is very, very small for one-dimensional ferromagnet is wrong. So we should not expect that delta m is actually small in one dimension because we estimate that this delta m diverges. Therefore, it's this kind of spin excitations are going to eat up all the spin moments you originally have at t equals 0, so that as you go to this ground state and thermodynamic limits, and your net spin moment will become 0. Now, which makes the spin wave analysis failed, and which means that we cannot use spin wave analysis anymore because the correction becomes divergent, and this kind of small correction assumption is wrong. Likewise, for t equals to 2, you get the logarithmic divergence of delta m proportional to little t times log k0. When k0 becomes 0, you get, again, minus infinity, a log divergence in 2D. Again, so in 1D and 2D, in the thermodynamic limit, this spin flips events are really, really dominating over your original, alignment, perfect alignment configuration. So this is called Merben-Wagner theorem, which says that for 1 and 2 dimensions, this spin, flips event at low temperatures is going to destroy your long-range order. So there's no magnetic long-range order for Heisenberg ferromagnet in 1D and 2D. Okay, so that's really important message that this spin wave or spin flips events are going to destroy your long-range order in low dimensions. So we will come back to this next time when we study antiferromagnet, but let me just start to analyze this Heisenberg antiferromagnet. As we mentioned before, that the spins for the antiferromagnet arranged in such a way that this has sublattice structure, that all the sublattice A with the spins pointing up and all the spins on sublattice B will point downwards. Okay, but if you simply just do some spin rotation, that you rotate the spin axis around this x-axis by 180 degrees, so that the Sz becomes minus Sz and Sy becomes minus Sy, but Xx is still the same as Xx for just sublattice B. In other words, if I do this spin rotations around Sx axis, then I could flip this, the convention that I would define that spin plus 1/2 is actually point downwards on sublattice B, and then all the spins are just parallel to each other, which means that if I flip my spin axis on sublattice B in such a way that the spin down state in the original basis becomes spin up in the new basis, which I call this theta basis. And in such a way that the Heisenberg antiferromagnet could be rewritten in terms of Si in the original basis, but Sj in the theta basis. Okay, in the theta basis, this Sj minus becomes Sj theta plus. Sj plus becomes Sj theta minus. So you get plus 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 minus minus for this spin on side I and j respectively, and the Sz components still remain the same, Siz dot Sj theta z. Okay, so we will come back to this just a moment next time to actually study the spin excitations of an antiferromagnet after we perform such a spin rotation. Okay, so I'll see you next time.